Alright, so for this last video for gas laws, again, this is something that we saw before. This is Dalton's law of partial pressures. And basically what this is saying is, if I have two containers and they're both the same volume, so let's just say they're both 5 liters, and they're at the same temperature, they're both at 298 Kelvin, then what I'm looking at here is, like, let's say in the first sample, I just have O2 gas. And in the second sample, I have O2 and N2 gas. Well, the idea with partial pressures is the total pressure of the mixture is equal to the partial pressure of each gas in the mixture. And so this kind of goes back to something like with gases, when they collide, that's what causes pressure. But the gas doesn't care if it collides with a gas molecule or the wall of a container. A collision is a collision, and the collisions are considered to be perfectly elastic. No energy is lost, there's no attractive forces between the gas molecules. And of course, this isn't always true, but it's an assumption that works fairly well. Like it's not too far off. When we get into extreme pressures and temperatures, then it doesn't work. But what I look at is if I have a mixture, the total pressure is going to be equal to the sum of all the partial pressures of the gases in the mixture. So gas A, B, and C. So this question says, what is the total pressure exerted by a mixture of 4.05 grams of nitrogen, 3.15 grams of hydrogen, 6.50 grams of helium, when the mixture is in 6.10 liters of space at 25 degrees Celsius? So we want to know total pressure. Well, the total pressure is going to be defined by the total moles in the sample. That's really what we need to find. All of the moles are in the same volume container at the same temperature. So really what I need to do is find the total number of moles of gases in the mixture. Rather than figuring out the pressure of just nitrogen, the pressure of just hydrogen, and the pressure of just helium, and then adding them all together, which I can certainly do it that way, it's a shortcut to just figure out how many total moles I have. So if I have 4.05 grams of nitrogen, 1 mole of nitrogen is 28.02 grams, molar mass from the periodic table. So if I quickly divide those two, I get 0.145 moles of nitrogen. Same thing, 3.15 grams for the hydrogen. 1 mole is 2.02 grams from the periodic table. So when I quickly divide those two, I get 1.56 moles of hydrogen. And then for the helium, 6.50 grams of helium. 1 mole of helium is 4.00 grams from the periodic table. So when I divide those real quick, I get 1.63 moles of the helium. So if I add all of that together, 1.63 added to 1.56 added to 0.145, I'll round this to 3.34 moles, right? Just keeping my decimal places. So now what I know is I have that many moles total in my mixture, and of course those are the moles that are causing the pressure. So pressure would be nRT over volume. So my total number of moles, 3.34, R 0.08206. Temperature in Kelvin would be 298 after we add the 273, and volume 6.10 liters. So I've got my 3.34 times 0.08206 times 298, and then divide by 6.10, keeping 3 significant figures. I'm just going to type it in really quick one more time. Yep, I get 13.4 atmospheres for the pressure. Now, if you did it differently, what you could do is for each one of these, you could find the pressure of the individual gas. So if I have 0.145 moles times R 0.08206 times temperature of 298, divide by a volume of 6.10 liters, My partial pressure of the nitrogen is 0.581 atm. I can do the same thing for the hydrogen. If I have 1.56 moles times 0.08206 times a temperature of 298 divided by a volume of 6.10, I get 6.25 atmospheric pressure for the hydrogen. And then if I do the same thing for the helium, 1.63 moles times 0.08206 times 298 divided by 6.10, I get 6.53 atmospheric pressure. So if I went that route, then what I could do is just add up my three individual pressures, my 0.581, my 6.25, my 6.53, and what you'll see is that we get the same answer either way. So when I add these three together, I get 13.4 atmospheres. So the reason why it worked to just find total moles is because the R constant doesn't change, right? Temperature doesn't change, and the volume doesn't change because they're all in the same container. The only thing that changed in those three gases was the moles that were present. So if I'm looking for total pressure, it's because of the total moles. So I just had to add up all of my moles and solve once for pressure rather than doing each one individually. But that is the law of partial pressures, right? That the total pressure in the mixture is equal to the individual pressures of each of those gases added together. All right, so where does partial pressures come into play? Typically, obviously it comes in when there's mixtures of gases, but typically partial pressure questions are going to come under the guise of collected over water problems. All right, so when you see that phrase, right, that a gas has been collected over water, you probably remember this from intro, the gas is bubbled up through water. And what happens is water in the gas phase is trapped inside the mixture. So when you're given the pressure for the sample, it's really the sum of the pressure that you were collecting added to the pressure of those trapped water molecules, because again, those trapped water molecules are leading to some collisions. So they're contributing to the overall pressure of the mixture. So what you'll have to do here is to figure out the pressure of just the gas you're collecting. You're going to have to take the given pressure and subtract that pressure that's due to water. And you know, the pressure due to water, the great thing about that is that it's temperature dependent. So we have tables, vapor pressure of water tables, vapor just meaning gas. So when you see VP, that's vapor pressure or gas pressure. And as long as we know the temperature that we're at, we know the pressure due to water. So here's an example. We're going to collect hydrogen over water. We're at 17 degrees Celsius. The total pressure inside the collection jar is the atmospheric pressure in the room, which is 738 torr. The volume is 246 mils. What would be the mass of the hydrogen collected? So if we're looking for mass, right, we're thinking we need to get to moles first, right? This is going to be a Pivnert question. So we have PV equals nRT, where we're going to solve for moles and then take it to mass. Now temperature, 17 degrees Celsius, but when I add 273, that becomes 290 Kelvin. My R, 0.08206. Temperature, or sorry, volume in milliliters, I have to convert to liters by dividing by 1,000, so 0.246 liters. And so this is what makes it a collected over water problem. When it gave us the pressure of 738 torr, that was the pressure of the hydrogen and water combined. So what I need to do is subtract the pressure due to water, and that is what we get from the table, right? But we were given to it here in the question. So for the homework, you're going to have to look it up in the table in the book. Vapor pressure of water at our 17 degrees Celsius is 14.5 torr. All right, so when I take my 738, which is the sum of the two gases, subtract out the water, I'm going to get the pressure of just the hydrogen inside. And that's in torr, so I need to divide that by 760 to get to ATM. And I'm going to now, whoops, sorry, that didn't type in right. Now I'm going to round to three significant figures, yeah, and I get 0.952 ATM. All right, so that would be the pressure of just the hydrogen gas. Now I'm ready to solve. If I look for moles, right, PV over RT is equal to moles. Pressure 0.952, volume 0.246 liters, R 0.08, 206, and temperature in Kelvin 290. So if I take my 0.952 times 0.246, divide by 0.08, 206, and divide by 290, I'll figure out that I have 0.00984 moles of hydrogen. And because we want mass, molar mass is 2.02 grams for the H2. So when I multiply that by 2.02, I get 0.0199 grams of hydrogen gas. So that would be my mass of hydrogen that I collected. All right. So another example question here. We're going to take potassium chlorate, KClO3. We're going to decompose it, which produces oxygen gas. The oxygen we're going to collect over water. We're at 21 degrees Celsius. So I'm going to go ahead and just convert that to Kelvin. And we know the vapor pressure of water is 18.7. And we start with a pressure in the room of 746 millimeters of mercury. But again, that's going to be a pressure of the oxygen and the water that's trapped inside. So we're going to subtract that pressure due to water. All right, now it's different from the last question we looked at because we're at a different temperature. At 21 degrees Celsius, the vapor pressure is 18.7. But back here, we were at 17 degrees Celsius, and that's the pressure then is only 14.5. So we're going to subtract 746 minus 18.7. I get 727.3. And I'm going to go ahead and divide that by 760. And I'm going to convert this to ATM. So I get 0.957 atmospheres. So that's the pressure of just the O2. All right. Now, we have also a volume of 0.155 liters. It gave me it in milliliters, so I just divided by 1,000 to get to liters. What we're looking for is to figure out the mass of potassium chlorate. So we're doing some stoichiometry here, right? We're going to go from an A to a B. What I always need to figure out first is the moles. When we're looking at a gas laws question, the only way to get moles is to use PV equals nRT. So gases have to have a lot of information. In order for us to understand how many moles or molecules there are in this reaction, I have to understand the pressure of my gas, the volume, and the temperature. All three of those to get me to moles. So PV, I'm going to move over here, over RT will get me to N. The pressure of just the oxygen gas was 0.957 atmospheres. The volume was 0.155 liters. R, 0.08, 206. Temperature in Kelvin was 294. So this will be my moles of the oxygen gas. 0.957 times 0.155, divide by 0.08, 206, divide by 294, 0.00615 moles of oxygen. Now I can do some stoichiometry, right? If I have 0.00615 moles of O2, now I can go to my mole ratio, getting rid of O2 on the bottom, going to KClO3 on top. Coefficient for every 3 moles of O2, I need 2 moles of potassium chlorate. And then the question was looking for mass, so I need the molar mass of KClO3. So 39.1 for potassium, 35.45 for chlorine. 3 oxygens together would be 48. So 122.55 would be the molar mass there. So now if I take, sorry about that, 0.00615 times 2 divided by 3, and then times 122.55, I had 0.502 grams of potassium chlorate. So that would be the mass of potassium chlorate that I decomposed. So for stoichiometry with gases, unless you're at STP, you have to go through Pivnert. So we had to know all of our conditions for the oxygen gas. It was collected over water, so we subtracted the vapor pressure of water to get the pressure of just the oxygen. And then, of course, convert that to ATM because we're using Pivnert. We have our volume, our pressure, and our temperature. So now we can figure out how many moles are present. Once we know the moles of oxygen produced, we can figure out through the mole-to-mole ratio how many moles of potassium chlorate we started with, and then using molar mass, how many grams that would have been. So we had about 0.5 gram of potassium chlorate in this reaction. So that is stoichiometry, and again, the center point is always the mole-to-mole ratio. It's just what's different here is that, with solids, we typically measure mass, so molar mass gets us to moles. With solutions, we typically measure volume, so molarity gets us to moles. With gases, we have to measure everything, just about. We have to know pressure, volume, and temperature, because all of those are related if we're talking about moles. We need to know all of those variables. So with gases, there's always going to be a lot of numbers, a lot of measurements. But just understand, anytime you're doing stoichiometry with a mole-to-mole ratio, you're going to have to be going somewhere either to or from Pivnert, right? Because Pivnert is moles. Just make sure that when you're using Pivnert, you have the moles of the gas, right? Because Pivnert is obviously a gas loss question. All right, so there's one more stoichiometry question, or two more, sorry, on the next page. We've got a decomposition of calcium carbonate. We want to know how many liters of CO2 at 825 degrees Celsius, 754 torr, are produced in the decomposition of 45.8 kilograms of the calcium carbonate. So in this case, the mass of our solid is our A, the volume of the gas is going to be our B, right? That's where we're headed. So we have 45.8 kilograms calcium carbonate. We know to go to moles first, but we need molar mass, which of course is in grams. So just real quick, I'm going to multiply by 1,000 to get to grams. Calcium carbonate, I'm going to add 40.08 for calcium, 12.01 for carbon. 3 oxygens would be 48. I get 100.09 grams for the molar mass of the calcium carbonate. Now I need my mole-to-mole ratio. So for 1 mole of calcium carbonate, I'm going to produce 1 mole of CO2. And that's going to be my N that I can plug into Pivnert, right? That's my moles of gas. So I have my 45,800 grams divided by 100.09 molar mass. So I have 458 moles of CO2. Now I can use Pivnert. Volume will be nRT over P. I have 458 moles of the CO2 gas. R 0.08206. Temperature, don't forget to convert to Kelvin. 825 added to 273 is really 1098 Kelvin. And then I need to divide by my pressure, and of course it needs to be an ATM. So I'll take the 754, divide by 760. It's really 0.992 atmospheres. And that'll go in my denominator here. So volume will be 458 moles times 0.08206 times a temperature of 1098 Kelvin, divide by a pressure of 0.992 atmospheres. And it's a large number, as you would expect. It is 41,600 liters of carbon dioxide. All right, so anytime we do stoichiometry, right, we have to go through the mole-to-mole ratio. In the last example, we were starting with the gas, so we did Pivnert first to figure out moles, then the mole ratio, then to mass of solid. This one was the opposite. We were starting with mass of solid first. We went to moles. That was our N. Now we plugged into Pivnert. Last question for stoichiometry. We've got the same reaction, but we're going to change it, and now we're going to be under conditions of STP. And what we want to remember is that means 1 mole of any gas will occupy 22.4 liters of space. So when we're at STP, we have a little bit of a shortcut. We have that 45.8 kilograms, just like we started with. We'll go to grams first. Molar mass, 100.09, will get us to moles of calcium carbonate. Now we do our mole to mole ratio, which is 1 to 1, 1 mole of calcium carbonate, 1 mole of CO2. And at this point, we could do the exact same path that we did up here. We'd have our N. If we stopped now, it would be the same, 458 moles. And we could plug in the Pivnert. Our moles, our temperature would be standard temperature of 273, and standard pressure would be 1 atm. So we could do it exactly the same way, just changing temperature and pressure accordingly to STP. Or we can do a little bit of a shortcut here. Because we're at STP, we know that that mole of CO2 will occupy 22.4 liters of space. But again, this is only because we are at STP conditions, otherwise we can't use that. So I'll take my 45,800 grams, divide by 100.09, times 22.4, and now in this case I get a volume of 10,200 liters of CO2. All right, and that's because of course the temperature is much higher. We went from 273 Kelvin up to 1098 Kelvin, so that's why the volume is so much larger in the first example. All right, so for stoichiometry, remember you have to go through the mole to mole ratio. If you're at STP for gases, we do have a little shortcut that looks just kind of like molarity did for solutions, right? 1 mole is 22.4 liters. It'll convert moles and volume. But if you're not at STP, you've got to go through Pivnert. The last part of the chapter talks about kinetic molecular theory, right? I need you to read this. This will be kind of conceptual information, but basically gases are mostly empty space, which you knew. Kinetic energy, energy of movement, is proportional to the temperature. So the higher the temperature, the higher the kinetic energy. And collisions are elastic. I mentioned that earlier, meaning that when they collide, they don't lose any energy. They just keep bumping and going and bumping and going. All right, so that is an ideal gas. Gases are not always ideal. When you start having extreme pressures and temperatures, then they don't behave that way. When they're at high pressure or low temperature, what you think about is those molecules start to become very close together. And that's when that ideal behavior falls apart. They can start to have what are called intermolecular forces, and they will now sort of attract and repel with one another because they're closer together, and then they don't behave ideally. And velocity, diffusion, effusion. Velocity is speed, and it's inversely proportional to molar mass. So basically, lighter gases move faster, which to me just always seemed like, yeah, that makes sense, right? So hydrogen, right, if you can imagine, that's our fastest gas, right, H2. So the lighter it is, meaning the lower the molar mass, the faster it will move. Diffusion and effusion is looking at how the gas flows, where diffusion is it diffuses into another space, whereas effusion specifically, it flows through a small hole in the container. But all of these are related together. The heavier the gas is, the slower it will move, right? And then Graham's law of effusion actually looks at a mathematical approach, looking at the square root of the molar mass. I tend not to do the mathematics here with Graham's law of effusion, but conceptually, I do want you to remember, right, the lighter the gas, the faster it will move. The higher the molar mass, obviously, the slower it will be. So anyway, that is the end of our Chapter 6 notes.